My dear students of Design of Concrete Structures 1, CE703, today we will be discussing about shear stress and shear force dealing in the concrete beam. Previously you have learned about bending moment and shear force in a homogeneous beam. The material was single one, and in reinforced concrete, as you know, it's a combination of cement concrete and steel. Previously we have dealt with the bending, and we have designed bending tensile steel for moment, and now we will be dealing with shear failure. And in shear we will be providing the section depending on the strength of the material and the shear force, and the shear force that is to be taken care by this concrete section. And in reinforced concrete we take shear by two materials. We take care of shear by two materials. Some part of the shear is taken by concrete and some part is taken by steel, like the bending moment. There also we use these two materials combined for taking compression and tension. Here we have shear stress or shear force. The shear force will be taken care by, some part of this shear force will be taken care by concrete section, and some part of the shear value will be taken care by steel. Because if we do not use steel, the shear failure will be a sudden failure, which we never want. Therefore we will be using concrete and steel for taking some part of shear, and the steel will take some part of shear. And in this design method, we will be using shear by concrete section and also by the stirrups or steel vertical stirrups, is shown in figure 7.1, and the section is shown on the right side of this figure. Stirrups supported by in the section B of the figure 7.1, vertical stirrups are shown in the beam long section, and in the cross section of the beam the stirrups are shown like this ring. This is also known as a ring by the workers. The stirrup is normally used. The stirrup is provided by number 3 or 2, 4, 5 bars, because it is to be bent, and the stirrups should be some limitation of spacing. That's why we will be using the smaller size of the steel bars for shear taking, and some part of this total shear force will be taken by concrete to give the concrete a certain section, so that this section can take care of moment also. Because if we use this section very small, then both the tensile steel and shear reinforcement will be required more. And if we go in intermediate way, then some part of the shear will be taken by the concrete section itself, and some part will be taken care of by the stirrups itself. Now we will discuss this whole thing with the help of an example. Before the example, we require we are to take care of some part of this problem, that how much amount of shear can be taken by the concrete itself, and that is given in page 4, the first equation for BC permitted by ACI code. If we decide about a section, in designing the beam from shear consideration, the beam section can take care of certain amount of shear that is given by the ACI code equation. Vc is equal to 2 lambda root over f prime c bw into d. Here lambda is the aggregate factor. It is whether it is a stone aggregate or is a brick aggregate. On that basis, this lambda factor will be given. For stone aggregate, the lambda factor is 1, and for brick aggregate, lambda factor is 0.85. And you know f prime c is there under root. The f prime c is under root. Therefore, always you have to put f prime c in psi. You cannot put it in KSI. In most of the cases, we will be giving the f prime c value as KSI, but when you will be using this f prime c in any root over, then you have to put this value in pound unit. And BW is the width of the beam, and D is the effective depth of the beam. So, in this equation, we have shown that how much shear force will be taken care by the beam section. Here the factors are the beam section, BW, and D is the cross section, F prime is the concrete strength, and lambda is the aggregate factor, and 2 is coefficient, and this much shear force will be taken care by the B into D section. Equation for vertical stirrup spacing is when we will be using stirrups, we have to find out the stirrup spacing in the beam, horizontal spacing, and thus that S is the spacing dimension in inches, and phi is the shear reduction factor. For shear, we have previously discussed that for shear the phi value is 0.75. AB is the area of the shear reinforcement we will be using in a section, and that will depend on the size of the shear reinforcement, and always there will be 2 legs of shear reinforcement. That is why we have to multiply the cross section of the shear reinforcement by 2 to get the value of AB, and FYT is the required. FYT is the strength value of the steel we will be using in this shear reinforcement. Here we have introduced a term FYT. Previously we used FY. Now we will be using for stirrup or shear reinforcement as FYT. FYT stands for transverse reinforcement. The shear reinforcement is also known as the transverse reinforcement. That's why here, and we will be using the lower grade of steel for shear for stirrups, because we want close spacing of the stirrups. That's why we will be using lower strength of steel. Then that will give us a closer spacing of the stirrups. And D is the effective depth of the beam. BU is the calculated shear force for the section we will be for which section we will be trying to find out the spacing of the stirrup. Accordingly, we have to put this value 5 VC, and we use the value that here is the value we will be calculating from the formula. I'm sorry, the VU we will be calculating from the beam longitudinal section, that is the shear diagram, and phi is again the reduction factor, and VC is shear stress. So if we use this equation, VC this phi VC. So if you use this equation, S is equal to phi AB FYT D divided by VU minus phi VC, then we will be finding the spacing in inches. Spacing in inch. Now here is some limitation of this spacing of the shear reinforcement. ACI code and other organizations give some limitation of this spacing. That's so much we cannot use spacing more than the spacing specified in these three conditions here. The first condition is ABFYT divided by 0.75 root over F prime C BW. Then again there is another condition, ABFYT divided by 50 BW, and there is another condition, S max is equal to D by 2. Calculating these three values separately, independently, in separate way, we will choose the minimum of these three values for the maximum spacing of stirrup in a beam. And this much of theory we must know for designing a shear reinforcement in the beam. And number one is the BC. Number two is the spacing equation. Number two is the spacing equation. And number three is the maximum spacing relations. There are three relations in this maximum spacing. Number one is a formula related one, and in the middle there is a D by 2 factor, and at the end of these three figures is 24 inches. And this much of knowledge we must have in designing the shear reinforcement in a beam. And about the beam section, we have as the concrete can take only VC is equal to 2 lambda root over F prime C BW D. If we use this equation for finding out the section of the beam, then that will be a very big one. And we cannot construct a beam without shear reinforcement, because if we construct any material only with concrete, then there will be a brittle failure, a sudden failure will be there. That's why we will be using shear reinforcement. And for shear reinforcement, we have stated the equation of S, spacing of the stirrup. Now we will be finding out all this, use these formulas with the help of a direct problem of a beam. We have chosen a 25 feet beam for this example demonstration, and per running foot the load is 6 kip, and the other values are F prime C is 3 ksi, FYT is 60 ksi. Here we will be giving FYT, and we will be using FYT as lower value than the tensile steel. In tensile steel we use normally FY as 60 ksi. In shear stress we use 40 ksi, so that the spacing of the stirrups remain closer. That's why if we use higher strength, the spacing will be much bigger. Then in that case the minimum spacing will be controlling. So we have to now go for finding out the shear reinforcement and the spacing of the shear reinforcement. For that we will be, first of all we have to calculate the shear force. Maximum shear force is at the support, and this is WL by 2, and this gives a value of 75 kips at the support, and at the middle of the beam the shear will be 0. Here maximum shear is at the support, which is WL by 2. W is 6, L is 25, and that divided by 2 that gives 75 kip load. Let the width of the beam, we have to we cannot keep two unknowns in a single equation. That's why we have to assume someone, and then the other dimension will be coming from the relations. Here first of all we have to choose the beam width. Sometimes we will be getting all these dimension of beam from moment consideration. In that case we didn't have to assume values. But here, as we are not related this problem with moment dealing, here we have to find out first of all the beam width. Otherwise we cannot solve this problem. In normally the beam width in a building is 10 to 12 inch width. Therefore here we have kept the beam width as 12 inch. We have taken beam width as 12 inch. And now for keeping the section of the beam to a practical dimension, in the the beam, the equation for section and the shear value is Vu is equal to 4 lambda root over F prime C Bw into D. This is the general equation with respect to shear value and the beam cross section F prime C, etc., etc. And this is the general equation for shear with other factors. So now we have the Vu here is 75 kip means 75,000 pound. Because here is a prime C is under a root over, we are to place the prime C in pound unit. We cannot put this in kip unit. Though we have mentioned the concrete strength as 3 kip KSI, here we have to put it as 3000 PSI. This 4 value varies from, if we here use 2, then there will be a weak section, and that section will be taking care of full shear stress, because we want to keep this beam in a reasonable dimension. We should not use this 2, and without shear reinforcement we cannot design a beam. That's why we will keep this section to some smaller value. For that we have put this 4 as the coefficient, and lambda is the aggregate factor. Here with the F prime C is 3000 psi, and we suppose that the concrete is made with stone aggregate. That's why we have put this value of lambda as 1, and concrete strength is 3000, and it, as it is in under root, it will be in pound unit. And we have already decided about the width of the beam, that is 12 inch, and now the unknown is D, and we have, by solving these figures, we have found this D value as 28.5 inch. This is the effective D. Now we have to add with this one the Clark-Kavar, etc., for finding out the total dimension of the beam. Normally, in such a beam, we will be expecting 2 layers of rod, though we don't have any calculation, but we will use 2 layers of rod, and for 2 layers of rod, we have to, for finding on the total height, we have to add 3.5 inch with the effective depth of 28.5, and total depth comes as 32 inch. And we will be constructing this beam. We have to construct this beam with a dimension of 32 inch, and the width is 12 inch. So again, we have to find out the effective depth, though this is the same, because we have the dimension has come to a round figure. Again, after reducting from 32, 3.5, the cover dimension, the effective depth remains as 28.5 inch. Is it okay? Again, here the thing is very new to you, and that's why I will be repeating this value. We have found the maximum shear as 75 kip. We have assumed the beam width as 12 inch, and we have a general equation for Vu with respect to concrete strength, beam section, and concrete stress. And that equation, in that equation, some factors are constant, like lambda, F prime C, Bw, and D. And the coefficient 4 or 2 or 3 or 8, we can, if we want to keep this section a little bigger, then we have to use this coefficient smaller. It starts from 2. If we use 2, we will not be requiring any steel, and the section will be a big one. If we use this value as 4, the section will be an intermediate one, and we have to use some reinforcement, etc. And if we want to keep this section little more, then we have to change this 4 value to 6, 7, 8, and we cannot use this value more than 8. There is a limitation of this one. In that case, this section will be too small. Now, on the average, we will be taking this coefficient as 4 or 5 or even 6, nothing more than that in practical cases. Therefore, we have decided, just to give an example, this value we have chosen as 4. And now we have to find out how much shear force can be taken by this section, which we have decided here is 28.5 into 12. And only concrete can take a force. The equation is same. Here we have to use phi value and also a coefficient of 2 in the equation. The big equation, we have to use 2 as the coefficient, where the concrete will be taking this force. After calculating all this a long line, we can explain this one. Phi BC, that means the how much shear force will be taken care by the concrete is given by phi. Phi value of shear force is 7.5, and 2 is the coefficient to find out the shear taking capacity of section. And F prime C is there, BW is the width of the beam, D is D, and we have put this numerical value, and at the end of the calculation we have found that there is 28.1 kip load can be taken care by the concrete section without any reinforcement, and the remaining forces are to be taken care by stirrups. And there is another point, that in a beam, though in calculating the shear force WL by 2, we use L as the total length of the beam. Actually, shear fails a distance D from the face of the column. That's why we will be calculating the value at a distance D. Now we have decided about D. At a distance D, what is the shear value? That is the critical value. For that critical value, we will be providing stirrups. Here in this case, our shear at the support is 75, reaction at the support is 75 kip, and D distance is 28.5 is the depth of this beam, by 12 is the distance, and that multiplied by 6, and calculation of this gives us a value of 60.8 kips. We have to calculate the shear reinforcement for the 60.8 kip only, not the 75 kip. And this is the critical one, and this is here will be the stirrups will be closely spaced. These stirrups here we have to use closely spaced stirrups. Now we have to decide about the size of the stirrup. Normally 3/8 inch or 1/2 inch bars are used in shear reinforcement or stirrup calculation. The 3/8 inch diameter bar has an area of 0.11 inch, and as there will be two legs, as we have shown in the previous figure, there are two legs of a shear reinforcement, then we have the area provided is 0.11 into 2 is equal to 0.22 inches square. Now spacing of stirrups. For the spacing of stirrups, there is a equation, standard equation, which is phi AB FYT into D divided by V critical minus phi VC. There is a derivation for this equation, but it is very too complicated, and that's why I have not gone to that detail for finding out this equation. We will be using this equation as a formula, and that will serve our purpose. So we have to know what are the factors here. Phi is reduction factor for shear, that is 0.75. AB, we have decided that 3/8 inch rod will be used, and there will be two legs. That's why 3/8 inch rod has an area of 0.11 that multiplied by 2 is 0.22. We have put this 0.22 in the numerical portion of this equation. FYT, we have decided that we will be using 40,000 psi concrete. 40,000 psi steel. That's why we have put here 40. And all these dimensions are in kip. That's why FYT is also in kip. And depth is previously decided is 28.5. And our critical shear was as calculated earlier, that is 60.8. And the shear capacity of the beam without shear reinforcement is 28.1, and that's why after calculating these numerical values we get 5.75 inch, and we will be using 5 inch center to center. We could have used also 5.5 inch, but here to be more sure, more safe, we have taken this value as 5 inch center to center. And there are some limitations or the requirements that the maximum spacing of stirrups will be how much. We have previously noted the formulas there and relations there. Now we will be calculating all those values from the beam dimension consideration. Here S max AB FYT divided by 50 is a requirement, and BWD is there. AB is again 0.22, 0.22 is the area of stirrup of 2 legs. One leg is 0.11, 2 leg is 0.22, and FYT is 40,000, and 50 is 50, BW is 12. After calculating it, we got it 14.7, and that is equal to 14. We will be rounding it to 14 inch center to center. Another requirement is D by 2. Here our D is 28.5, and that divided by 2 is 14.25. That also gives us a value of 14 inch center to center. And there is another requirement, S max, that is equal to 24 inch. That's why here out of these three conditions, we have to choose the minimum one, and the minimum one is 14 inch center to center. Use maximum spacing as 14 inch center to center. This 14 inch center to center will be required where there will be shear will be smaller, and that's why at this middle of the beam where shear reduces to 0, and there is some value from middle towards the support, the shear force increases. We have to use this 24 inch center, this 14 inch center to center near the center. And as this beam is symmetrical, load is symmetrical, that we will design only the half portion of this beam. And that's why the shear force where near the center, the spacing will be 14 inches, 14 inch center to center. For this 14 inch, how much shear force is required, or for what value of shear force as spacing of 14 inch will be coming in the spacing equation, we can find out in the reverse way of that one. That is, we have to first of all put this 14 inch in the equation of finding out spacing of shear. In the top of this page is that equation is there. The equation is 0.5 into AB FYT D divided by V critical minus 5 V shear. And here we have to put this 0.75 is 0.75, the steel is AB is 0.22, FYT is 40, and depth is 28.5, and the VU is the ultimate shear force, and 28.1 is the here in this equation 14 is the spacing of the maximum spacing of the beam. For this 14 inch spacing of the stirrup, how much shear force will be required for this 14 inch center, keeping all the dimensions same. Here 0.75 is phi, 0.22 is AB, 40 is FYT, 28.5 is DT, and BU is the unknown shear force, and the concrete section can take 28.1, that is put, that value is here at the bottom of this equation. And if we transform this value and find out there is one equation, the only unknown is VU, we can find out this VU. Yes, VU. We can find out this VU from this equation, and the value comes as 41.5. This is an arithmetic calculation, you can understand this one. We to cross multiplication from 14 into VU minus 28.1 into 14 gives 393.4, etc., and the value is 188.1, and that divided by this 14 is, the value comes as 41.5. That means where the shear value in this beam is 41.5, there will be required, there we can provide a spacing of stirrup as 14 inch. This 41.5 kip shear on the beam is at a distance from the zero shear point, can be calculated like this, because this 41 is the force and 6 is the shear per foot. 6 is the shear force per foot. That's why the distance from the support, it is where the 41.5 kip shear will be coming, is 6.92 feet. The remaining space is 12.5 divided by 12.5 minus 6.92, that is 5.58. The 41.5 shear is at a distance of 6.92, and remaining space is 5.58. Now we have to put this kip shear is a distance, can be calculated where it is. This 41.5 is, if we divide this 41.5 by 6, we will be getting the distance from the support 6.92, and remaining space is 5.58. This 5.58, and we can divide this into two spaces for changing the shear reinforcement spacing. For the first 3 feet, we have already calculated that this shear spacing is 5 inch center to center, and for the later 3 feet, we can find out the spacing of the stirrup from the general equation, where phi is 0.75, AB is 0.22, 40 is FYT, and 28.5 is depth, and this 57 minus 57 is the shear capacity of this section, minus 28.1, and that gives you the shear spacing of 6.5. That means from practical consideration, the arrangement of stirrups are as finalized below. From practical consideration, we have used this first 3 foot spacing is 5 inches, middle 3 foot the spacing is 6.5 inches, and the rest 6.5 the spacing is 14 inch center to center. Thank you.